Hello everyone, welcome to the 18th episode of Math and Beyond and this podcast. Today we are going to talk with the, again, I hope to get this right, with the Theo Karydas, should be easy, Theo Karydas, about dark matter and how to probe dark matter using gravitational waves. And Theo graduated with his from a master in cosmology at the University of Amsterdam. And so today we are going to discuss this topic. I'm going to send him the invite now, and I will see you shortly. Hi, Theo.
Hi, Francisco.
Hi, how are you?
I'm doing all right. How about you?
I'm doing fine. There is some good weather today in Amsterdam, so yeah, it's a great day whenever there is.
Right. Yeah, that's always very good there.
Where are you at the moment?
I'm actually at Amsterdam right now.
Okay, cool. Yeah, then how's work going?
Sorry, can you repeat that?
Yes, how is work going?
It is going all right. So I'm part of this journal right now, and there's a lot of papers to publish.
Okay. So quite a busy period at the moment. Well, that's at least I think that's what we like with regards to this maybe. I think so. So I give a small introduction.
Where they publish a lot of things.
Sorry?
Summer is the period where there's a lot of conferences and very active for authors to publish.
Okay. Also, where are you from Greece?
I am.
Okay. Yes, I can say from the accent. I do sometimes this accent that either I associate it either to Greek people or to Spanish people. Yeah, very similar. I don't know why.
I can see the resemblance. Yeah, there's surely something there.
Okay, so I gave a small introduction about the topic of discussion of today. We are going to talk about a little bit of dark matter and gravitational wave, especially how to probe the first one using the latter. So how to probe dark matter using gravitational waves. And I also gave a small introduction about you. You already mentioned that you are working for this journal, and your academic background is that you obtained your master's degree at the University of Amsterdam in gravitational and astroparticle physics. Is that right?
That is right.
Great.
At the University of Amsterdam.
Okay, then I think we can jump into the topic of discussion of today, and I would like to ask you firstly to very briefly introduce gravitational waves, very briefly because we already covered it with actually a PhD student who is a GRAPPA member, who dipped but Vaj, and we talked about gravitational wave. So just very small introduction of gravitational waves. What are they?
Right. So I think gravitational waves are very non-intuitive to understand for as humans, that we cannot really observe them. And the best way to minimally describe them, I think, is by comparison to other waves that we know. Right? Waves at the ocean, which are perturbations of the seafloor at its height, or sound waves, so perturbations of air, the density of air. And gravitational waves, in a sense, are the same, but they're a little weird. They're an outlier in this comparison, because everything else happens, well, it evolves in time, and it's a perturbation that travels in space. But gravitational waves are really a perturbation of the space-time itself. Yet they are still traveling somewhere, and they can have a source somewhere far in the space and come here on Earth and detect them and tell things about them. So this is something very weird that is cool to think about. But these perturbations were predicted by Einstein over a century ago, and they can come from many different sources. What I like to focus on is binary black holes, right? We have detected a lot of them. There are black holes that circle around each other, and they emit gravitational waves. And in this process, the waves carry energy and momentum from them, and in turn they merge. And the way that the black holes merge depends very sensitively on the waves that are produced. And the waves also depend very sensitively on how the black holes merge. So there is a connection there that we as scientists use to learn more about these events that produce the waves in the first place. So there are many other ways to find or to produce gravitational waves. So from inflation in the early universe or from neutron stars. And all of this associate very heavily to the properties of the system that produced them in the first place. So, if it were black holes, you can start the discussion about their masses, their spins, so how fast they rotate or how they rotate with respect to each other, since they're a binary. If they have any charge around them or an accretion disk, if they're in empty space, any stars around them, even in the vicinity very far away from the merger or very close there. It's a neutron star. You can talk about, well, its shape, it has any mountains, or its equation of state, which is a big mystery in physics. We can talk about it if you want later. It's a topic I hold dear. But right, there is a lot in gravitational waves. They can be very, very different from each other, depending on the source and the different details. So there is a lot of work to be done to, even if we detect them, to discriminate from each other and understand what is going on there.
Okay. One very useful intuition, as you mentioned, which I think at least helps me to grasp it. At least I think quite neatly is when I see videos of, I don't know, known famous physicists or cosmologists talking about gravitational waves, they always refer to gravitational waves as the ripples on a pond. Okay, you drop a rock, ripples on a pond. But the thing is that one may say, okay, but then light is a wave, so also light, isn't it? The ripples in the pond. The problem is that the pond, in our case, is the space-time itself. Okay, and the gravitational waves indeed are those ripples, let's say, that the pond is experiencing. Whereas, I don't know, light, let's say, light can be literally any other wave arisen from, I would say, any other type of phenomena, not of the pond itself, though, because those are indeed the ripples of the manifold of our universe. And so this was indeed our very brief introduction of gravitational waves. And I would like to ask you, what about instead dark matter? We start quite strong in a matter of 5 minutes, giving an introduction about gravitational waves and dark matter. What is instead dark matter? Why there is such a thing as dark matter? How did we find, or actually, how did we understand there was such a thing as dark matter?
Right, I think that's the last one is a better question. I have no idea what it is. It's very fascinating to search about it. But I think dark matter is a collection of evidence of something that we cannot yet describe with our physics as it is right now. But it seems to make sense together. So different independent observations that are discrepancies to our models, somehow they create this beautiful picture of something new. So dark matter, we usually understand it as particles, right? That exist in the universe. They probably, I know there's some 80+% of the matter in the universe, and we cannot see them. So the main idea is that originally people looked at galaxies and the stars around them. And they found out that these are moving much faster than they should be moving. The concept is that, well, we can see stars and we can gauge how heavy they are. And for a system that is gravitationally bound to itself, we can calculate through Newtonian dynamics even how fast something should be moving, because we know the mass that it rotates around of. But this seemed to not make any sense, and stars were rotating much faster than they should be. And at some point, physicists made this argument that perhaps there is something that we do not see that is contributing to the mass, that explodes this gravitational well and makes it much larger to align our observations with the theory. And this is where the dark matter came from, at least the strongest argument.
Okay.
We can see this in many galaxies, everywhere in all the galaxies, I suppose. There is what we call the dark matter halo. There is this discrepancy of something that behaves as though it is a mass or a density, let's say,
okay,
particles. And these are dark because we cannot see them, so they're probably not interacting with electromagnetism. So they must be interacting with gravity. And maybe something else that we're not sure about yet. It's dark matter is all about questions, having questions that you try to answer.
I really like your. It was actually the first time I heard someone literally starting an explanation on dark matter, saying it is a collection of evidences. And it's actually right, because at the end of the day, we really cannot say what is it, it is not. You just know there is something. And actually, that's also why you probably said you like the last question the most, because it's actually the only question that makes sense. We don't know what is it. We know there is such a thing as. Okay, and that's I really like it. Okay.
So there are so many different theories about dark matter, which is fascinating. So many different ways to explain it.
What do you think, let's say, do you believe a very, let's say, important concept that people go through when trying to explain dark matter is whether there are, let's say, sort of extra dimension that we cannot see, that dark matter interacts with? Do you believe that may be the case? Just pure intuition and speculation. Because to be honest, at this point, like when I think about it, I say, okay, it does not interact. Basically, it only interacts gravitationally, and we cannot see it. And gravity, guess what? Is the only force, quote unquote, is the only force that we cannot explain through the standard model. So there is something ongoing here. Okay, something sneaky. I don't know that is messing around with us. What is your I don't know, your intuition, your belief with regards to this?
Oof. Right. So I think this is right, that we cannot explain gravity, and there are all of these attempts to create the graviton and whatnot. But at the same time, since gravity is this theory of geometry of space-time, the standard model itself works on top of space-time. So we might need at some point to untangle this to make sense. The question might be wrong, let's say, to explain gravity through the standard model. But other than that, I think that indeed higher dimensions could be an answer. But I'm not quite an expert on it. And from what I can tell, it's a beautiful theory that is stretching our understanding of the universe very thin. There is probably, for example, in string theory, you can have a lot of dimensions, which could be a way to explain all of this. But by stretching thin, I mean that there are probably better candidates out there that we can first exhaust and see if they are, so dark matter candidates, if they are dark matter or if they are not.
Okay.
Or we start looking at higher dimensions. In the sense that, from my understanding, I'm not sure if there is any concrete experiment to probe higher dimensions other than looking if forces from higher dimensions are leaking into our own 3+1. So there's right. There's a lot to think about. There is a lot to think about. I think theorists working in higher dimensions should continue to work up with an experiment that we should try at some point after exhausting other options.
You mentioned that, of course, we have an hypothesis of higher dimension, but we do have many other theories trying, of course, to explain dark matter. Can you expand a bit on some of these candidate theories? What is the most, let's say, suitable? What is the one that we believe the most? So what do we believe? Actually, let's say, what are we most biased to believe dark matter is?
Wow. I think if you asked someone 20 years ago or 30, they would tell you that the wimps are probably dark matter in the universe. The wimps are winkly interacting massive particles, which are essentially what we call cold dark matter. You know, from our observations, we assume that dark matter only interacts gravitationally with everything, and it is also not interacting with itself or with any other force, with baryonic matter, you know, ourselves, or things that we can see, and that it is moving non-relativistically, hence cold. So WIMPs are a subset of this cold dark matter that can also annihilate with each other. So if they come very close, you get an explosion into the standard model. So you get light or particles that come out. So it's a process similar to matter-antimatter annihilation that happens. And WIMPs were very, people were very biased to find WIMPs and created many experiments or looked at the sky for evidence for many decades. Because there is this interesting coincidence that happened with them, what we call the weak miracle. Or at this point, physicists were looking into the weak force and trying to understand the weak nuclear force. So there are these forces in the universe: electromagnetism, the strong, the weak nuclear force, and gravity. And we still did not understand this very well. And it seemed to be the source of many discrepancies in particle physics models. At the same time, cosmologists realized that they knew about dark matter. And they realized that maybe there is no way to create matter from dark matter and vice versa. So in a sense that all of the dark matter that exists today existed at the birth of the universe, because there is no way to exchange the quantities between these two. There is no window or door for one to walk and become the other.
That's also known as the baryonic asymmetry. Universe, right?
I think so.
Okay.
And the idea here, at this very early stage of the universe, is that all of the dark matter was created by some mechanism, but also there might have been a way for dark matter to become matter, and these two to find a balance with each other. So if there was a window for an interaction between the two, an interaction that would create particles from one to the other, this would be more possible during the early universe when everything was hot and warm and very close to each other. This is what opens up the whole idea about the relic density of dark matter, that all of the dark matter was created back then. And at some point, as the universe started to cool down and expand, this interaction paused. It, as we say, froze. And at that moment onward, no more particles can interact with dark matter. Well, this is the basic idea behind it. But if you try to make sense of it in physics and mathematics, you find that these particles, in order to explain how much dark matter exists in the universe today, which would have been the same back then when this freeze out happened for the relic density, it has to be that the strength that mediates this force is the same as the weak force. So this is the miracle. The fact that at the same time, there were a lot of discrepancies in the weak force and dark matter in the universe, we came to think that there may be a connection between the two. This is what led many physicists to search for dark matter as they were searching other things. And many of them build experiments just for dark matter. I think overall WIMPs have, are very infamous today for not finding them after so many decades. The best that we could do is say what WIMPs aren't, or how aren't WIMPs, if you want. I said WIMPs, but this is a collection of different theories of particles that exist that the theorists can make, and there are dozens, if not hundreds, of different modifications. And we're trying to look with our experiments which of these combinations of theories, or theories themselves, aren't explaining what we see in the experiment. And in this sense, we're just cutting off theories and cutting off the parameter space, as we call it, of the WIMPs.
How do we plan to detect WIMPs? So how do we plan to detect dark matter in general? And what are the experiments, let's say, designed to detect what would be our theoretical WIMPs?
Mm-hmm. Right. So, I talked about those particle physics experiments. These are essentially accelerators that take or some of them take particles, baryonic particles, accelerate them, and at high energies, they see if there is any evidence that dark matter was produced. There are also ways to look at particles that sit around in a pond or some space that we can monitor very well, and look if they interact with some way, with some passing dark matter particle that just happens to go through Earth, for example. And there are also, those are both indirect detections of dark matter, because we do not see dark matter itself, we see what it does to particles. But there are also direct detections of dark matter, and those are physical in nature, or at least for the WIMPs. Because they are self-annihilating, it means that if you have WIMPs that are very close to each other somewhere in the universe, so at the center of galaxies or around black holes, which they tend to cluster, you would expect to see a signal, right? So if you look there, you would see light or particles coming from that source, where you see nothing other than that light. So you do not see evidence of stars or gas and stuff like that, that you can relate the light that you see otherwise, or the particles. And this is the only way that we have hoped to directly detect dark matter, as far as, or the WIMP dark matter, as far as I know. And like the others, it has only resulted with us more constraining more tightly the theory, because we do not see anything, or what we see is very weak and could be explained by other reasons. So probably if WIMPs are out there, they're even more weakly interacting than previously thought.
Okay, but
this is what has been done in the past. Now there are probably new avenues to detect them, even with gravitational waves, which was the topic of the original discussion.
Exactly. So we are not here indeed to talk about yes, we are here to talk about dark matter, and but not only per se, because we want to, let's say, go through what is the new, let's say, tool for probing the astronomical, astrophysical objects and events in the universe, which are gravitational waves. And I would like to ask you indeed, relating to this, how can gravitational waves be used to infer the nature, to probe the nature of dark matter?
Mm-hmm. I think overall there are three ways to detect them, or to categorize them in 3 ways, or 3.5 ways, maybe. You can detect, there are 3 sources of gravitational waves. You could detect the gravitational wave background. So this is gravitational waves that were produced during inflation, the very earlier stages of the universe. And they carry information about dark matter, which existed there and became the seed to form galaxies later on, which was able to cluster. And these waves, what we say is that they are continuous, in a sense that it is just the background that is mixing with itself, but it has some properties. So it's frequency spectrum. So what modes go into it, how fast these waves are moving or are described, but not really an actual speed in space, but the frequency of the wave. This carries this information. And at the same time, there are also gravitational wave bursts that can happen from this early universe. And this relates to theories like string theory, where you can have something and, well, something else happens. So this is what we call a phase transition. Essentially, your theory, your potential changes. And this is not a real potential, it would be an effective potential that describes the event that you see. And in this change, you are allowed to produce more energy via gravitational waves, which is due to gravity, to cool down your system, in a sense, but produce them in bursts, meaning that they just happen and then they go off in the universe in their own direction, instead of being produced for a very long time, as we see with black holes, or as it would have been the case with the gravitational wave background.
Okay.
The other 2 ways to look at them would be through black hole mergers and their influence on gravitational waves that are produced normally in the universe today. So black hole mergers can spiral around each other. But if a black hole sits at the center of the universe, the gravitational wave will pass through some dark matter that clusters around the universe at very long scales from the black holes. And this will microlens the gravitational wave. Microlensing is is one of the ways that we originally found out about dark matter, but in terms of light. So the idea is that you have an object, light passes through, and it changes a little bit. For example, we can see stars behind our sun, just because the light of the star comes and bends.
As you Albert Einstein.
But gravitationally. And the same can happen with gravitational waves, just it happens with light. And so if gravitational waves pass through dark matter, they will change a little bit. And we can detect this change, or we hope to detect this change, either way, to learn about the properties of dark matter eventually. Now, I say that we hope because we actually have to be more precise and accurate with our experiments on Earth.
What do you mean with the change in gravitational waves passing through dark matter? Or at least, what is the change that we hope to see in gravitational waves passing through dark matter?
Okay, so unlike with light, it's not that it's going to bounce and miss Earth because it was lensed from the dark matter, but the phase and the amplitude of the wave is going to change. So it's going to get smaller in the sense that this energy is diluted because it does not pass through empty space, but it is passing through something very dense, in that sense, the dark matter that exists between us and the source, presumably. And the way that the wave is going to change, so you do not expect to see anything drastic, but just very small changes that you may be able to find out if your source takes a long time to end. So if you could see, for example, 100 or 1,000 cycles from a given source, you could say that, the way that these cycles are drawn on my interferometer do not make sense if they pass through empty space. So they might have been lensed, if that makes sense from my lensing theory. So if they can match.
Okay, so basically what we are, let's say, hoping to see here is we detect a gravitational wave, we predict it, let's say, we theorize it through general relativity, we observe it. If we see discrepancies, then we may say, okay, something is going here.
Yeah, that's correct.
Okay, so basically we are looking for general relativity, let's say, breaking with regards to gravitational waves. Okay.
Right. Yeah, we call these exotic waveforms because they do not conform to our models or the original ones for the vacuum space. And this is actually a model for detecting dark matter, depending on how it propagates in space, right? Because its propagation changes its signal and imprints dark matter properties into the gravitational wave that we can then extract. But there is also a different way where the dark matter itself influences the production of the gravitational wave at its source. So instead of having dark matter very far away, you have it where the black holes merge. And in this sense, you can have some very dense regions of dark matter that influence the motion of the black holes while they merge. They usually will make them merge much faster. Why? Intuitively, you can think of it like having a string and a ball attached, right? And I can do this motion and have the ball move around my hand. Well, try to do the same motion with your hand inside of water. How much more difficult it is going to be to make the ball move. In this sense, the balls would be the black holes, which they experience friction from this dark matter density around them. So this would be gravitational wave friction at the very least, which we call dynamical friction. They can eat some of the dark matter. So in the process, their mass becomes larger. And if dark matter interacts with the world in any other way other than just gravitationally, you could see that also. So if dark matter has a pressure or a temperature, you can see that because it will interact with the black holes differently. If there is a magnetic field, you could see that. And if dark matter is a wave or a field, for example, we didn't cover this, but there are many different types of dark matter for particles that can be very small or very large. And all of these different things can imprint themselves differently into the production of the gravitational wave, just by how they interact its particle with the black hole as they merge.
Okay. One very recurring, let's say, topic or concept that I would encounter when, let's say, getting some stuff ready for this talk is the concept of a primordial black hole, which sounds funky term. What is this primordial black hole? Do we have any in our universe? If yes, let's say, if yes, and if no, in any case, how do we theorize they originate these black holes?
Right. Black holes could be those very big particles that I briefly mentioned. They are, they are black holes in nature, and we have not detected any of them yet. But unlike the ones that we have seen, which we consider to be stellar and are, the corpses of stars that become very big, and at some point at their end of their life, they collapse and form a black hole in some cases, normally. Primordial black holes, on the other hand, were formed during the very early universe.
How?
Well, what we usually think about is that the universe was uniform, as in matter was very uniformly distributed out there, as we can see from the CMB. But at the same time, there were different fluctuations, density fluctuations, because uniform does not really mean that equal. And as the universe was expanding, some of these densities were heavy enough to create primordial black holes, to collapse under their own weight and create something that from which light cannot escape. Okay, so this is what black holes are, in a sense, a region where light cannot escape from. And these regions, if you create them, then it is very hard to destroy them. And from what we know, there is only one way to do that. And this is what we call Hawking evaporation. So primordial black holes were created back then from this reason. And you can come up with different theories that are resulting with primordial black holes of different mass spectra. So either very big primordial black holes or very small primordial black holes, when they were created. But the universe is billions of years old. And today, or when we look at the sky, at some redshift, which happened in the past, those primordial black holes that should have been there must have survived this Hawking radiation, which makes them evaporate, as we say. So they are losing some of their mass in a process that is somewhat similar to black body thermal radiation. What we see, anybody with temperature emits something, emits light. And this is somewhat similar to black holes, to what we call Hawking radiation. And it's much more efficient when your black hole is small in size. So if your primordial black holes were very small originally, they might have evaporated. But some primordial black holes might have still survived in the universe at the time that we observe them. And they are black holes, so there's no light coming off from them unless they have some matter around them, like an accretion disk. So if those black holes are sufficiently small to not have an accretion disk, we will not be seeing them. And if they do not have a magnetic field, we would also not be seeing any evidence that they exist somewhere, which is why we think that they could be dark matter. The fact that at least they would be interacting with gravity, because they are figments of gravity in a sense.
Okay.
Right. And unlike particles, you would expect primordial black holes. There are many different experiments that look for primordial black holes. We haven't found any yet. And the reason is that they can have a very wide range of masses. They can be, sufficiently small. For example, they could be grams or meteor-sized, or they could be thousands of solar masses. And we would not be able to tell in that sense. Probably the best way, to describe them would be if we found any gravitational waves from black holes, or if we found black holes that are subsolar, we could say that, those are probably primordial black holes. And if we find primordial black holes that are very small in size, they might be able to be dark matter, because then they would be able to be many particles of them, many primordial black holes, in order to get this 80+% of dark matter of the mass be dark matter in the universe. and explain the effects that we see on galaxies and those different types of evidences. So instead of having very small particles, you would have some, well, very heavy, but still small particles. But there would be, fewer of them out there.
Okay. But, okay, first of all, I want to ask you, why don't these black holes created in a very early universe don't start eating so much matter that they just, let's say, keep on living? Let's say, how can it be we are having, let's say, black hole evaporates when we know these objects literally rip apart every piece of matter they encounter?
Well, they can do that, and we know through the CMB how matter was distributed in the early universe, and we can use this depending on the theory that resulted in a primordial black hole of a given mass to describe how much of other mass was accreted around it, and this goes into the calculation of how much has evaporated since then, because it does keep eating, but at the same time, if it's very small. So if you had a very large black hole, it would not evaporate. And also its reach is much more, is much larger, it's much more efficient in accreting mass around it to it. But if you had a very small black hole, the problem is very different because evaporation operates much faster timescales, meaning that there is a lot of black hole that you lose at a given moment. And the black hole itself can only reach so far that if there is no matter around it, it will have a problem because it cannot replenish that. So there's a very elegant balance there that you have to take into account. But what's very cool is that sometimes primordial black holes, they can be dark matter, but they could be a type of dark matter. So if primordial black holes exist, and there is also more types of dark matter out there that are cold, this could also accrete around black holes, the primordial ones, and form some very packed regions of dark matter around the primordial black holes. In that sense, you could get away with even smaller sizes, because unlike accreting regular matter, which in the early universe disperses, does not cluster because it's very hot. Dark matter clusters with itself and would cluster around primordial black holes. And so these packets that would be formed in the early universe would feed the primordial black hole during its evolution.
Okay. How do we instead detect these primordial black holes? Because we already did for some bigger black holes, quite bigger. But how would we do it with primordial black holes, if they are so tiny?
What happens with gravitational waves is that we could detect them with gravitational waves, for example, and for them, the smaller the mass of the object that emits them, the higher the frequency that will be emitted. So what happens here is that we have to build new detectors in order to see them, if they are very small, or if they are stellar mass sized, which black holes are typically not. We just have to wait to see them. So with primordial black holes, most of the time, it's about building new experiments that are more sensitive to events that are very rare or very weak, or to a frequency domain that we have not yet explored with our gravitational wave interferometers. So those big lasers. And well, this is one way to detect them. The other is just looking at the sky and how the galaxies are distributed. In this argument that primordial black holes exist, which might probably exist, that we haven't found them yet, then there is probably also dark matter, other forms of dark matter existing alongside, which, as I mentioned earlier, would cluster around them. Depending on the properties of this dark matter, you could expect to see even catastrophic changes to the shape of the universe today, which has helped us overrule some of these effects. So what am I trying to say? If you had, say, dark matter or primordial black holes and dark matter that are wimps, that are self-annihilating, those we know that dark matter clusters around itself in the early universe. And if there was a primordial black hole there, it would cluster even strongly. What would happen is that the wimps would come closer together and annihilate so fast and so much that they would heat up the universe as it expands and disrupt the creation of galaxies as we know them today. So this argument helps us construct universes, so mock universes with simulations, using this amount of energy that would be inputted into the galaxy if wimps were a form of dark matter alongside primordial black holes, and compare them to our actual observations of galaxies in the universe, and realize that this would not match. That, at least for wimps, this is a new way to overrule them. And at the same time, it is a way to overrule how primordial black holes are distributed in the universe, because of this argument that there must be more dark matter out there.
Okay. And we also, at least I've also, read about, while getting ready for this talk, I was reading about some people proposing, modifications to the laws of gravity at large scales. What do we mean by that? What are these theories, and how would they help us explain the nature of that matter?
Yeah, I think we discussed a lot that dark matter as a form of matter, of particles, where originally I introduced it as a series of evidence. But you could probably also play the game of what is dark matter differently, and that is through these modifications. The idea is that instead of coming up with new particles, masses, or whatnot, that you try to tweak our understanding of the universe, or laws of nature, like gravity or conservation of energy, to come up with the effects, to explain different effects that we see out there. For example, in the argument of the galaxies and the stars that move very fast, you observe many galaxies and you find out that all of them have this same behavior, which is why we say that dark matter is not unique to a single galaxy, but it's probably to every single one of them, and it causes the same effect to everything. So what if this effect was not a new mass, but it's just how baryons, how stars behave, but we did not notice them before? So these modifications are usually in the large scale, where accelerations of objects are very small. So gravity is very weakly interacting, which you can guess that we have not been able to probe very sufficiently, because we know gravity every day here on Earth. We know it at the solar system or at the inner galaxy range. But at even larger scales, does it work as it's supposed to? So these theories propose to modify Einstein's theory of general relativity, or even Newtonian dynamics. So this would be modified Newtonian dynamics, to accommodate for these different effects. And they were very popular at some point. And I think this is the second school of thought that tries to describe dark matter, because they can come up with a coherent story that describes many of these evidences together, like microlensing or the velocity curve, so how fast, how stars and galaxies move faster than they should be moving. But at the same time, I think that their charm has faded recently or in the last years, alongside with wimps. Why? Yeah, so over 20 years, so in 2006, we observed two clusters merging together, which by some demonic coincidence, we were able to calculate, to both see those using light and calculate how much baryonic mass there is there, and at the same time look at how much dark matter mass exists in those clusters using microlensing, so gravitational lensing from some light that came behind them towards us. And what we found was that using those two different methods, that where the particles are, where the stars are, is not where the mass of the system is concentrated at. So if you picture this, if you were making a theory of modified gravity, you would say that no, there's no more particles. We're just not understanding gravity very well. But even if you do this, it is very hard to make a theory that changes the center of mass of something. And our understanding is that, well, there is no modified gravity, or if it is, it must be something very specific. And at these two clusters that merged, that pass through each other, actually, the stars, let's say, collided with each other. And through this, while dark matter did not. So dark matter was able to move forward and cluster in a different place than the stars of the clusters did. And I think this is the argument that sole-handedly deleted many of these Mond theories. They discarded them, and which is why they lost their charm.
Okay. Do you believe should we modify our laws of nature to explain? Because, well, there is also to say that we are talking about dark matter, but there is also something which is probably even more mind-boggling, which is dark energy. So at the end of the day, we know that with our theories, we know to explain 5% of the universe, what we know there is in the universe, which is quite ridiculous, I would say. So do you believe we need to modify our laws of gravity or in general of nature to explain these effects?
I think absolutely we should try. We should leave no stone unturned. So things may not look good right now for this, but this does not mean that it's not the one true theory. We just think we need one thing to work out in the end, and to be able to explain all of the different evidences that we see and we're going to accumulate in the years to come. So, and this may not be some theory that is pretty or it makes sense or at the same time solves the problems with the weak force or Sepe violation or whatever other problem that exists in physics at the time. In a sense, I think that people doing this should continue to do this work. And all of us as a community should focus on a specific candidate and work it through. Okay.
Also, many episodes have been, let's say, involving the use, the role, the implication that machine learning has in these studies, in probing the nature of whatever we are trying to probe the nature of. And I would like to ask you, how does actually machine learning enters the picture here? How does it help us simulating, for example, effects that black holes may have or black holes embedded in layers of dark matter. How does machine learning help us? If it helps us.
Right. Well, I think as a fan of machine learning, that it probably can help us with a lot more than just that. It does change everyday life, and it can do any calculation that seems difficult much easier. So usually, what happens with machine learning in gravitational wave science is the same with what has been happening so far in gravitational wave with dark matter in our mind. The idea is that usually to detect a gravitational wave, we look at the signal, and then we have to match the signal to our prior understanding of how the wave would look like. So the problem is that in most of the cases where we detect a signal, the signal is going to be buried in noise that is going to always be there, or noise that will be a burst, like a car passes by, or something happens in your instrument, like something moves and causes a signal to be made. Those things we have to discard normally, and to discard them, we need to know what we expect to see, which is anticlimactic in a sense, that we need to have this very good knowledge beforehand, and we then just confirm that this exists in the universe, other than seeing something new. So to get those waveforms already, to have this knowledge, we have to simulate them. And this is usually a process that takes a very long time. So for solving general relativity, you have these fancy words that describe that. You have differential equations, which are tensor equations. And when you try to simulate black holes and the gravitational waves that they emit, it's just a nightmare that can take months of CPU time in a cluster, depending on the system that you try to simulate. This is horrible because when you do eventually observe the gravitational wave, you need thousands or millions of waveforms. And imagine for a single system, if it were to take millions of 1,000 waveforms, for which a month or even a day was to be needed to simulate them, we would be missing so many signals, or we would be, our progress in gravitational wave physics would be much slower than it is today. So one avenue to go around this very slow generation of equations is to use machine learning. And the idea is that you can solve, you can get a collection of waveforms of a system, or a collection of physics if you want to, and train a model to understand these things by varying different parameters of the system. So in the case of black holes, you can vary the masses, the spins, the distances, or if you have exotic waveforms, the outcome is just endless of what we can do. And well, the more parameters you have to vary, the more waveforms you need to understand what you're looking at. So the need for machine learning is increased when you do train the network. You can then probably, if done correctly, predict outcomes for you. So predict waveforms. This is what we call the surrogate model. And it is one way to assist in this process. A different way would be just to say that, well, we need those waveforms in the first place because we want to match them with what we get, what we observe, and create probability distributions through some very rigorous statistical processes, which are what require those millions of waveforms. But we could also train the neural network, the machine learning network, to do this process instead. So maybe you don't even need to generate thousands of waveforms. If you can just look at the signal and have the machine learning tell you, yes, this is a black hole with this and this mass, and it merged this time ago at that part of the universe. And I think those are the two main ways of using machine learning, which are relevant in the detection of dark matter through gravitational waves. Because just like in trying to solve general relativistic equations, you would have to solve those or even similar equations, but with dark matter. So an even more complex system that takes a long time to simulate.
Okay.
Machine learning severely can enhance this process so that you get a result in a reasonable amount of time.
Okay. What are the most common machine learning algorithms? I mean, in general, if you can say in general, but maybe for some specific task, I don't know, for example, either classification or.
Yes. So in general, in gravitational waves, you may want to use classification to look if your waveform is exotic or not. So if there is dark matter around the black holes, or if there is no dark matter, and this could be a quick way to do it. But at the same time, you may want to get how much dark matter is there, or is it wimps? Is it clouds? Is it something else? Primordial black holes? What is it exactly? For this, we usually use regression other than classification, for which, and for classification itself, it's usually neural networks that do the trick. Another very versatile tool that can be trained. So far, I think that there haven't been very fancy in terms of Google type neural networks that we see in the news in the gravitational wave community. Partly because they already do a lot of work. Even the simple neural networks, assuming that you have a lot of data, or that you can leverage the physics and the symmetries of the system to when you train the neural model, seem to be enough to do the trick in that sense. But there's also traditional machine learning that one can try to get very reasonable results. I think that what people have been doing a lot is they're using latent spaces to map gravitational waves into something that the neural network can understand better. So the idea is that if you look at a gravitational wave, it has three different parts. The in-spiral, the merger, where during the in-spiral, the amplitude of the wave evolves very slowly and it's almost constant. Then during the merger, when the black holes are actively very close to each other and merge, the amplitude peaks. And then you have the ring down phase, where a single black hole sort of wobbles in space and still emits gravitational waves until it becomes symmetric again, spin. This, you can decompose it into different parts. So an evolution of the amplitude of the wave in time and its phase evolution, or in frequency, if you want to do that. But it's not important. What people have been doing is look at different types of these packets, different time evolutions of amplitudes and phases, and try to compress the entire information into a single latent space, which is a compressed space that describes the entire event with as few numbers as possible, with as few bits of information that you want. This seems to be very powerful in the case of gravitational waves, of surrogate models, of trying to predict the entire waveform.
Why?
Well, usually people have been doing this, utilizing the symmetries of the system. So in most cases, gravitational waves can be rescaled with the mass of the system and their time evolution. And you can input this into your system when you train it and improve their, its power, its predictive capabilities in learning. So this is one thing that has been done, and it mostly has not been done without it, that it might be of use. But also, gravitational waves are very smooth in a sense that, you have heard of the chirp mass, and this chirp term comes up from the shape of the gravitational wave, which starts slow and then just goes up. So it's a frequency that just increases. And increases in a very smooth manner. So there are no surprises, even if you have some very crazy spin orientations between the black holes. This seems to be very efficient in doing that work. But though, if you do not have this, and say there are some discontinuities in your waves, this is probably much harder to do without trying to incorporate these discontinuities in your system beforehand. This is actually part of my thesis that I did for a certain dark matter environment around black holes. It causes the waves to be very weird, to be discontinuous in time. In the sense that, well, what I call discontinuous is that instead of the wave being very smooth and predictable, that right now its amplitude remains the same, or it just increases very slightly. At a specific point, it just goes up very fast. You see an abrupt increase. This indeed, you cannot very much, you cannot do through a latent spaces like that. But if you try to incorporate it through some scaling, so by finding where these discontinuities are, for example, to align all of them together, you can still use the latent space. But this is probably tricks of the trade that are not of a lot of interest.
Okay. What are instead main, at least with regards to simulation and use indeed of machine learning when simulating the effects of black holes around dark matter? What are the main challenges in this regards?
In machine learning specifically, right?
Well, I mean, also theoretic, let's say theoretic-wise, if you want.
Mm-hmm. I think it all boils down to, is what I'm doing correct? Am I taking into consideration all of the possible effects? And if I am not, can I gauge what I am not considering? The whole idea is that with gravitational waves, we have to have this prior expectation of what we are going to observe before we can understand that we observed it. And with dark matter, it is a big problem because there are so many different types of dark matter. And all of them will have unique effects. Some of them may overlap with each other. So if we did find a waveform which is exotic and cannot be described by GR at some point in time, there's going to be this discussion of, okay, is this a problem with GR or was it dark matter? And if it was dark matter and it happened to overlap, so there are two candidates that can explain this waveform. Which of the two is it? This we can probably never learn, but we can just continue on amassing evidence and at some point hope that all of them are magically described by the same theory, none other.
Okay.
I think it's very anticlimactic, but it is how it is with dark matter and just the entire unknown that it is.
Okay. And I would like now to ask you if you can explain us about one of the latest projects that we have in this space, in the observational side, which is LISA. What's going on with LISA? How does it work? And most importantly, I would say, what can we, or let's say, what we would like to see from LISA?
I think LISA has been like the holy grail of astrophysics and gravitational wave physics. It's been proposed so many years ago. And so this is, unlike the detectors that we have here on Earth, LISA will go to space. And it's going to be what we believe to be 3 satellites that point at each other lasers. And just like the experiments on Earth, we're going to measure the changes in distances of the length that the light traveled to reach each of those three satellites. The idea is that putting LISA in space, we can do two things. One is that we can put the satellites very far away from each other, which will roughly allow us to look at frequencies that are much smaller than what is available here on Earth. Meaning that we can look at black holes that are very large or black holes that are very far away from each other. And the other part is that being in space, we don't have to worry about many, and being a minimal design experiment. Instead of building a whole contraption, a factory around the lasers, we just have 3 satellites. We're going to eliminate a lot of the noise that is related to the experiments here on Earth. So overall, LISA will be able to observe, not things that we can observe here on Earth, but something very different. So those very low frequency gravitational waves, which can be a whole bunch of things. So for me, it is very interesting because as it is able to probe large black holes, it can capture these effects of dark matter that clusters around large black holes. And at the same time, probe the large distances, which is where environments around black holes become important, like accretion disks or dark matter environments that we cannot really observe here on Earth right now. So all of the physics that I've been doing is in a preparation for LISA to come, and for the community of physicists that do the same thing. Then you could also observe gravitational waves from our galaxy, from different stars, moving black holes, and everything, which is going to give a background that we have an estimate. So this, I call it background because we cannot disentangle every wave from each other, because they happened and they have been happening for such a long time that they just exist there, something that we cannot go beyond, that we cannot remove. And however, its properties can be dissected, and we can learn stuff about our galaxy and beyond that. And at the same time, there's also, due to this very much reduced noise that will affect LISA, we may be able to see the actual gravitational wave background, the one that comes from inflation, which, if we are able to see it, it will just open up a huge discussion about whatever we see. Is we really don't have a very good prior belief of what is out there in that background.
Okay. Well, when do you think it's going to be on, LISA?
So LISA, it's said to be launched in decade, so in the 30s, I think. But we're going to see. Yeah, I think there has been a lot of discussion about it, being better before we launched it. So try to redesign it, and we're going to see when it is launched.
Okay. I would also like to ask you, let's say this is more personal, let's say personal opinion. Let's put it this way. Sometimes when I think about this kind of stuff, and I have to remind myself that light and the speed of light is the absolute limit in our universe. I can't help it but having the feeling that it is very, very limited. And this kind of sucks sometimes, because we already know that the actual universe is actually much bigger than the observable universe that we can see through electromagnetic waves. And I just wonder what actually may be out there, because okay, we can see a lot, but given the amount of stuff we know there is and we cannot see, well, light does not sound to be a good medium through which communicate, at least for even greater scales. What do you think? First of all, what do you think about that? And second of all, do you ever think that we are missing, let's say, not a force, but another medium, which helps us probe faster, further, and yeah, let's put it this way.
Okay. That's a very good idea to think about.
Yeah.
I haven't thought it about missing something, as in, other than dark matter in the sense, which usually I think that, there's so many different types of dark matter that we are missing something, but I don't want to have my hopes on what exactly we are missing. So it might be that the standard model will change eventually. It can't be just that. It can't be. It cannot comply with gravity after all.
The problem is that I don't know, I don't remember who, but I've been watching video and they were discussing the fact that I think it was either Leonard Susskind, I don't remember, whatever, and they were discussing the fact that they made sort of a calculation. They estimated the fact that the actual universe outside the observable universe should be around 200, 220 times greater than our universe. And I don't know, I really I really think I'm missing I really think we are missing a lot, not something, not very little. We are missing a lot. Okay. So I don't know, is it cosmological, is it eternal inflation? I don't know. Is it a sort of a multiverse? Because at this point, what I believe actually, and the term multiverse, I think it's very actual. I don't believe it as in what people think, but I do believe there are other universes, because if we call it our universe, I do believe it is just to be called observable universe. If I want to refer to the let's put it this way, to the bigger picture, to the whole thing, then I would call it either universe itself, or I would call it universe itself. I wouldn't or let's say unobservable universe.
Entire world, and then the universe is the observable part of this world that we can see. It's just a bubble. And then for an observer whose bubble does not interact at all or overlap with our own, it would be a different universe. Well, in that sense, is that what you're talking about?
Yeah, and let's say more as a mathematically described, because now I am reading a book by Roger Penrose, and he's now going over manifolds. And what I think, like we know, Einstein told us that our universe is a four-dimensional space-time manifold, and so what I do think is that our observable universe is a four-dimensional space-time manifold, but it is precisely for this reason that we cannot see the other part of the universe, because it may be that the other part of the bigger manifold is actually defined in other dimension, not higher or lower, just different dimension that we cannot probe, because our part of the universe is four dimension. We have evolved, complexity and life has evolved within four dimension, and we cannot probe in five or two or whatever it is, or in any case different dimension. That's the thing. The mathematical object which represent the universe, sure thing is a manifold. Our local universe, the observable universe, is the space-time manifold Einstein taught us about. That's how I see it, because otherwise I don't really explain. I don't really believe actually that that's just it. That's all we can see and all there is. No, that's really not the case.
Right. I think believe is a weird word to use for physics and science, or at least for me, in the sense that I try not to have any prior expectations of what may be. and just be amazed of what does happen to be there eventually.
Yeah.
You know, following an idea through the end. And I'm more experimentally oriented in that, or you know, not that I try to build a detector, but the work that I do, I want it to be proven or disproven. In that sense, so I haven't thought about this, but it's very cool. But I don't believe there are more dimensions, probably because it would open up this rabbit hole of what else can you believe there is out there, and
So that's the thing.
evidence for it.
I think here is a sort of the not the catch of my reasoning, but I would say sort of where I wrap it up, because what I also thought was when always trying to yeah start my head around this kind of reasoning and thoughts. I was okay. Well, people ask, yes, why there was Big Bang, why there was whatever inflation, whatever. But I think that the question more fundamentally and also more mathematically is not why there was a universe, why there was the Big Bang, why there was a beginning. The question should be, why are there dimensions? Because dimensions are, let's say, the means through which things can happen and be described. Okay, so that's the thing. 3 + 1 dimension looks arbitrary, and I don't really have any reason to believe, or actually to think, or to be convinced of the fact that that's all. Nothing can emerge out of any other number of dimensions. That's really hard for me to be convinced.
It might be cool if there was some theory that would describe things just by pure geometry, and everything just falls into place, the standard model, you know, dimensions and whatnot. And you know why those dimensions are actually, you know, infinite, or, you know, as large as they are. And if others exist, why wouldn't they be large or be small? For example, you know, there are particle physics experiments where they try to see if any forces leaking from other dimensions, and they can, at least from the dimensions that would be able to probe with this experiment. The idea is that it appears to be creating those arguments to create bounds for the size of those dimensions. So for at least a subset of them, if they exist, they would be very, very small, as in that you cannot really transverse them, because they will not be infinitely large to fit something in them, or sufficiently large in that sense. But you know, that's a very good question. And also it makes me think of gravitational waves, for example. We say that they are perturbations on the space-time, on those 3 + 1 dimensions, but you can still observe them coming from a source to you, so they are moving. And then you can calculate this despite being on the dimension. So it's as much a question about why there are dimensions, but why there are things that depend on your frame of reference and stuff like that.
Okay. Yeah, I thought about this is a very stupid aspect of the okay, maybe gravitational wave are just we know that gravitational wave pass through everything. So they, in our manifold, they are sort of holomorphic function. So why don't we start sending a gravitational wave that can be extended holomorphically also to other part of the manifold, so that we can probe it maybe through gravitational wave. But the point is that, which makes me sad, is that the limit for gravitational wave, at least the speed of gravitational wave, still is the speed of light. So this thing of the absoluteness of the speed of light, I think that many people still have not realized how actually fundamental and intrinsic of our universe is, because everything, literally everything, is built upon that. If you take that out, everything crashes out, everything literally breaks apart. And so that's, I don't know, that's just, I don't know, I think it's just funny to spend some time thinking about this.
It's very interesting. My friend, the mathematics that describe or try to describe these things are beyond most of us most of the time.
Well, and that's actually another thing that. But that's very likely to be true. Well, that's one other thing that I have been discussing. That I've been telling with Jessica Turner, who she came, I think 2 episodes ago, and my thoughts was that do you know about Gödel incompleteness theorem?
In mathematics, right? Yes, you cannot describe any system.
Exactly. Exactly. It says that basically you cannot describe, you cannot prove any statement to be true. There are statements that you cannot prove. And that's pretty much what I thought. I mean, mathematics is, let's say, okay, I don't know if you think that mathematics is invented or discovered, but let's say that we derive mathematics. Okay, but at the end of the day, mathematics is the language that we defined while being on the manifold itself that we are trying to explain. And to me, that's literally Gödel incompleteness theorem. We cannot explain everything that happens on this manifold, okay? Because we derive the language through which we are explaining the manifold itself, okay, is derived by the manifold itself. It's not outer language, okay? So we cannot expect to explain everything. And that's, I don't know, probably this theorem can be extended to this kind of stuff. But I don't know, it just reminds me of that. And so, I don't know, that makes me, I'd say, puts my heart in peace and I say, okay, whatever, fuck it, we ain't gonna explain it. No.
Right. I totally agree.
Okay.
No, very. Those are very deep thoughts.
Okay, so yeah, apart from this, I think we can wrap it up here, Theo. Thank you very much. It was an extremely fascinating conversation. Thank you for being with me. Thank you for your time. So, and maybe, yeah, who knows? We may see again in the future for some other talk with regards to some Lisa-related news. Or, if any new results may come out, you may want to tell us about. It would be a great pleasure to have you again. So thank you very much, Theo. Thank you for your time, and thanks everyone for following along with us. This was Math and Beyond the podcast, and I will see you the next time. Ciao.